In my previous video, part 2 of the Diels Alder process, I discussed the regioselectivity, the fact that if you were to draw resonance, you have a partial negative on this carbon of your diene and a partial positive on this carbon of your dienophile. So in terms of how the dienophile approaches, it's likely that the ketone will approach down here in terms of the regioselectivity. So we will get our, in this specific problem, you'll get our ketone basically in a 1,4 substitution pattern relative to our uh, oxygen of the diene. So you can see these would be the favored regioselective products. The next thing we need to look at is endo-exo. When our dienophile approaches the diene, the electron withdrawing group, the ketone, can either overlap our diene or it can sit outside as the bonds start to form. It might seem counterintuitive, but the way this is actually going to work is our withdrawing group will overlap the diene as the bonds start to form. It may seem like that would be too sterically hindered, but it's more of an electronic favored process. We have the electron-rich orbitals of our diene interacting with the electron-deficient orbitals of our withdrawing group in the dienophile when you have the withdrawing group overlap the diene in that manner. And this is called an endo process. Exo would be when the withdrawing group, again, sits outside of that process. So the first one and the third one are the endo products. The second and the fourth are exo products. And the favored product is going to be the endo product. So overall, we're going to favor the endo product in which the negative and positive sections overlap. And so this is the favored process, these being the favored products. Notice that they are enantiomers. And I'm going to show you now kind of a mechanism on why we get those enantiomers in the endo process. If I were to try to draw this in semi 3 dimensions, we have our diene here, and we have our dienophile approaching down here, where there's the ketone and there is the methyl group. What's going to happen is we're going to form the new sigma bonds I'm going to indicate in red. And if our dienophile slides under our diene, what's going to happen is when that bond forms, let me put in my hydrogens over here. When that bond forms, these hydrogens cannot swing through the bonds that are forming. So they are going to move up away from the bond that is forming, and these pieces on the outside are going to move down. So my hydrogen would move up in a wedge, the methyl group would move down in a dash. The same is true for the other side. This hydrogen needs to move away from the bond that is forming, so it's going to be a wedge, whereas my methyl group will be a dash. As that bond forms, also, our carbonyl here, our withdrawing group, is going to have to move down away from the bond that is forming. Hydrogen is going to move up. So again, our carbonyl will be a dash. And on the other side, our methyl group will have to move up as the hydrogen moves down. And the purpose of this is we cannot have the atoms cut through the bond that is forming because it's a concerted process. So in an endo product, what you'll notice is if I were to draw a circle here, completing this diene into like a cyclic structure, I call these the outer substituents, and the hydrogens that sit inside here, I'm going to call the inner substituents. In a endo process, the withdrawing group is going to match the outer pieces. So if I drew my withdrawing group as a wedge, these methyl groups on the outside of my diene are going to be a wedge as well. Because this is a trans dienophile, the methyl group will be a dash if that carbonyl is a wedge. And so that is what the endo process is. Now, again, the dienophile can either approach from the bottom or the top of our diene. And so the other possibility would have been, let's draw this again, having our diene come from up here, and we would form, should use a different color there, that bond and that bond. Now, as that bond is formed, what's going to happen is my carbonyl is going to have to move upwards. It's going to have to move into a wedge. And this methyl group will also move upwards into a wedge so that the hydrogens can move down and not cut through the bond that is forming. So again, in an endo process, your withdrawing group matches whatever is on the outside. The exo process would be the diastereomer. The withdrawing group will be opposite of the outside pieces. So in other words, if my withdrawing group was a dash, those outer pieces would be a wedge. That would be the result of the exo process, in which we would have our diene and then our dienophile, where the withdrawing group does not overlap the diene as the bonds form. Because here, when these bonds form, this group here would have to move up, whereas these methyl groups would then have to move down. They would be opposite. And let's look at a few examples. So if I were to have something like this, and I were to add this dienophile, what would my product be? Well, this is a cis dienophile, so when I form my product, they're both going to be wedges, or they're both going to be dashes, because a cis dienophile would produce a cis substitution here. Now the question is, where's this bridge going to be? Where's this carbon going to be? Well, on the outside, we have hydrogens. Remember, the outer substituent pieces are going to match my withdrawing group. So in other words, my hydrogens would be out here, and this carbon, this bridge piece, would be a dash. And the enantiomer could happen as well, depending on whether this piece adds above or below my diene. So the other possibility would be those CN groups could be dashes. The hydrogens would be dashes. And the bridge now would be a wedge. Let's look at one more example. Whoops, one too many bonds there. Let's look at this. I have this piece here plus, let's do this cyclic structure here. What would my product be? Well, again, we have our general structure of our Diels Alder product. These groups are cis So we would get, let's say, both of them being a wedge, something like that. And then these groups are in the inside. So they're going to be opposite of our withdrawing group. They're going to be a dash. The hydrogens that are on the outside will match our withdrawing group. They would be a wedge, but you don't have to show them. Keep in mind, depending on whether this thing overlaps above or below the diene, you could get either an enantiomer. So the other possibility would be if these were wedges, this would be a dash. Now, keep in mind, I drew this a little different. The way I drew it right now, this would kind of align into the exo sort of product. But keep in mind when those pieces add, it's going to add endo. So you'd have your methyl groups here, and then this thing would approach more like this. So it would approach like this as we form our sigma bonds. But that is the endo-exo process. It's all about how the electron withdrawing group of the dienophile approaches the diene and how the withdrawing group, the stereochemistry of the withdrawing group is relative to the pieces within or outside of that diene. So again, when you have a reaction, the withdrawing group will match the outer pieces of our diene in the endo process, or it will be opposite of them in the exo process. The other way to think of it is whatever's inside of that diene would be opposite of our withdrawing group in the endo process, but it would be the same side in the exo process. Endo is usually the favored product. So this was a three-parter. The first part I talked about, the video that was the first part, I talked about a Diels Alder in general, how the reaction happens. The second part I talked about the regioselectivity. And then third part I talked about endo-exo. So we were able to do a reaction in which we had 8 different possible outcomes from a Diels Alder reaction. But by first determining the regioselectivity, we can narrow our process down to these 4 potential products. And then by looking at endo-exo, the exo products are not favored, the endo products are. So these two are the favored products based on regioselectivity and endo-exo.